Good day, everyone. My name is Ariban Yas Memon, and today I'll be walking you through an essential component of hospital infrastructure centralized oxygen setup. This presentation is a part of our biomedical instrumentation course, and we will explore how centralized oxygen delivery works, its types, components, and safety concerns. Let's dive in. To begin with, let's understand what a centralized oxygen system is. Hospitals rely on a constant and safe oxygen supply, especially in critical areas like ICUs, operating theaters, and emergency rooms. A centralized system allows oxygen to be distributed via fixed pipeline networks from a single source, instead of placing individual cylinders in each room. This ensures seamless delivery and minimizes manual handling, making care more efficient and reducing the risk of supply interruptions during emergencies. So instead of nurses running around switching cylinders during cold blue, oxygen flows in it just like electricity through wires. Simple, efficient, and life saving. Now let's break down the system into its key components. So it starts with the oxygen source, which could be a liquid tank, cylinders, or a PSA plant. The second one is the manifold system. Manifold system connects multiple cylinders for balanced supply. Then we have pressure regulators which ensure the oxygen is delivered at safe, usable pressure. The fourth one is the medical gas pipeline system or MGPS. MGPS carries the oxygen throughout the hospital. Zone walls allows us to isolate sections for maintenance or emergencies. If something goes wrong, the alarm system will alert its staff immediately. Finally, terminal units. The outlets in walls where oxygen is actually delivered to the patient are paired with the flow meters and humidifiers. Flow meters and humidifiers to control how much oxygen is delivered and keep it comfortable to inhale. Think of it like plumbing, but instead of water, we are sending a life saving gas with all the safety controls and checkpoint in place. First, we have cylinder-based systems most commonly used in smaller hospitals. These involve multiple oxygen cylinders connected via manifold. Manifold, like multiple cylinders connected through each other, so which ensures a continuous flow even when one cylinder gets depleted. This setup is cost-effective for limited use. But of course, someone always has to check when a cylinder is empty and replace it, so it's more labor intensive. Next, we have liquid oxygen tanks used in large hospitals. These cryogenic tanks store oxygen at very low temperatures. When needed, the liquid evaporates into gas and flows through the hospital. This setup offers a massive reserve of oxygen and reduced refill frequency. It's like having a big refrigerator full of frozen oxygen that we slowly melt and breathe. Lastly, there's the PSA plant or pressure swing adsorption system. This setup generates oxygen on site from ambient air using molecular sieves to separate nitrogen. It's especially useful in remote or rural hospitals or during emergencies when cylinders or tanks may not be available. You could say it's like magical oxygen factory that pulls air from outside and makes it hospital grade. All right. Let's take a closer look at this schematic. This diagram represents the complete oxygen supply setup right from generation to the delivery at the hospital, including built-in backup systems. We begin on the left side with the oxygen generators, specifically DOCS 200 units. There are two shown here running in parallel. These machines are capable of producing medical grade oxygen on site using the pressure swing adsorption method or PSA. This is our primary oxygen source. Next, the oxygen flows into a system buffer tank, which is optional. This tank acts like a reservoir, balancing fluctuations in pressure and flow and ensuring there's always a stable supply, especially during peak demands. From the buffer tank or directly from the generators, the oxygen flows through the pipeline network into the hospital, represented here by red H symbol. You can clearly see in this picture. This applies oxygen to all wards, ICUs, and operation theaters. There's also a cylinder fill compressor connected to the main line. This device fills spare cylinders with the oxygen generated on site. These cylinders can be stored and used as emergency backup. Now, let's move to the bottom right section of the diagram. This shows two level of backup systems labeled backup hashtag 1 and backup hashtag 2. Both are powered by HOBS. that stands for High Pressure Oxygen Backup Systems, HOBS. These are bank of oxygen cylinders connected in parallel. Interestingly, there's a note that says option to use DOCS system as primary backup in place of cylinders. This means that if one DOC unit is down, the other can act as a backup, reducing reliance on physical cylinders altogether. Diagram. This diagram represents a simulation setup for high flow oxygen therapy. It's training scenario using an intubation mannequin, a realistic model of human airway to study oxygen delivery and airway pressures. So starting on the top right, we have a high flow meter. This controls and monitors the flow of gases, specifically oxygen and air, which are blended and delivered in precise amounts. High flow oxygen systems can deliver flows of up to 60 liters per minute, which is far higher than standard nasal cannulas. So, from the flow meter, the oxygen air mix travels through an oxygen line into a humidifier. Humidification is crucial because high flow oxygen is dry, and without moisture it could irritate or damage the patient's airway, so the humidifier ensures the gas is warm and moist before delivery. The gas then pass through an interface which in real patients could be a nasal cannula, face mask, or ventilator tubing. In this case, it connects to an intubation mannequin simulating a real patient receiving oxygen. This mannequin helps trainers understand airway behavior, positioning, and how oxygen behaves inside the airway under different pressures. So there are two important pressure monitoring points shown here. The first is circuit pressure. This reflects the pressure within the oxygen delivery line before it enters the airway. The second measures airway and pharyngeal pressures. These are crucial to understand how much pressure the patient actually receives, especially in sensitive areas like throat and upper airway. Monitoring both points ensures that we are delivering oxygen safely and effectively. This simulation is not just about blowing air into a dummy, it's about learning how oxygen behaves in real clinical conditions, how pressure, humidify, and flow all interact. It's a powerful tool to train future healthcare professionals in safe and effective respiratory care. Centralized systems come with several advantages. They offer a steady oxygen supply, better control over pressure, and reduce the risk of oxygen running out during critical procedures. They also save space, no bulky cylinders beside every bed, and make maintenance more efficient. It's like moving from dozens of battery powered lamps to a single well wired lighting system. Simpler and safer. Lastly, safety considerations. With great power comes great responsibility. Since oxygen is highly flammable, we need proper fire alarms and extinguishers, especially near liquid oxygen tanks. Regular leak checks are must. Always use medical grade oxygen and make sure pipes and outlets are properly labeled and color coded. And of course, staff should be trained to handle emergencies confidently. Oxygen save lives, but if handled wrong, it can be dangerous. That's why safety is not optional, it's part of the setup. Thank you for your attention. I hope this presentation helped you understand the importance and working of centralized oxygen system in hospitals. Thank you.